In this video, we will talk about std atomic and what is called as lock-free programming. We will talk about various C++ memory orders such as sequential consistency, acquire and release, and the relaxed memory order. We will learn how std atomic can be used to prevent the race condition in a multi-threading environment. std atomic is very notorious for being misused, and we will learn why a lot of people advise to use a lot of caution when you are using std atomic. It has been famously said that using std atomic is as if you're juggling razor blades, and maybe you should not use them at all, and it's probably one of the most confusing concepts in C++. Okay, I might have made up the last code, but you get the point. Hello guys, welcome to my third video in the series of C++ multi-threading. This one is about std atomic, which is by far one of the most confusing concepts in C++, and honestly, it's probably the hardest video that I've ever created. So I hope you like this. Please go ahead and subscribe to my channel and also like the video, and let's get started. Let's start by a quick review of the problem of having shared variables. So imagine I have a function that increments a shared global variable 100 times, and then I run this function in parallel between 100 of threads. So 100 threads, 100 copy of this function get executed at the same time. They all want to read, increment, and write into G counter, and then afterwards we print the value. Now the question is, would the final value of G counter be 10,000, which is 100 multiplied by 100? The expectation is each thread takes the counter and increments it in parallel with other threads with no problem. But in reality, this is not the case because reading, incrementing, and writing are not atomic actions. And while one thread is trying to read and increment and write, the other thread might do the same thing in parallel, and that causes a problem. Basically, the operations of one thread get interleaved with the operations of another thread in parallel. So what happens, for example, is that these two threads start at the same time. They both read the value of 0, and then they try to increment and write. Now, although we had two increments on this variable, the result, however, is still 1. So if you have 100 increments with this model, the result is always 1, and it's not what we expected. And that's what's called a race between reading and writing. Basically, it would have been ideal if we could force the read of this thread happen after the write of this thread, so that this thread increments to 1, then this thread can increment to 2. But the situation is even worse, because even reading a variable may not be an atomic action. So you might read the first half of the variable in one memory operation, and then the second half in another memory operation. And then during this time, another thread might come in, read, increment, and write, so that when you go back and try to read the second half of the variable, the value of the variable is completely different from what we read in the first half. So the whole result would be completely nonsense and invalid. This is called race condition, and we talked about this in my last video, which creates undefined behavior, and we should avoid it at all costs in order to have a correct program. Now, there is other problems. So the code that you write goes through some compiler optimization, for example, reordering, loop unrolling, and then goes through some CPU optimization in hardware, for example, out of order execution, branch prediction, and then there's cache that does some more optimizations on top of this by prefetching and buffering, and only then the result would go inside main memory. So it looks like your system is continuously trying to optimize and modify your code. That means the code you write is usually not the code that is getting executed. The first simple memory model that we might have in mind is that multiple threads are running at the same time, and each can read and write from memory directly. But this usually is not the case. There's usually multiple levels of cache between threads and memory. And what happens is that when a thread writes something, it only writes it in cache, and then there might be a huge penalty for other threads to see this result, because that result has to go through memory and come back to this thread, or you have to run some sort of cache coherence algorithm. So what is the solution? How these problems are solved in C++ programming? The first solution that comes in mind is to not share at all, so that you don't have any problems. While this seems to be a very simplistic and maybe impossible advice, but perhaps the lesson is that even if you have to share, try to minimize your sharing, try to have as few shared variables as you can so that you have fewer problems. Next, as we saw in the previous video, there's mutexes and locks, and we learn how to use critical sections to address the race problem. In this video today, we will talk about STD atomic and memory orders as another solution to solve the problem. And finally, there's something that I call abstraction, where you use high-level abstract constructs to deal with the race problem. And basically, your program, whatever you write, would be converted to constructs that use STD atomic and mutex automatically, so that by construction, your program will not have race. Some examples of libraries that try to do this are Intel TBB library, CSP and actors model, or MapReduce. Now let's focus on today's concept, which is STD atomic and memory order. Let's go back to our incrementer example where we want to increment this variable from multiple threads. And as we talked before, increment is really three actions: read, increment, and write. And we want to shield our thread so that during this time, nobody else can write and have race with our thread. And basically, this is what STD atomic does. As soon as you declare xint to be atomic, what happens is that read, increment, and write will happen atomically. So basically, the first thing that STD atomic guarantees is that this operation would be run atomically. That means we can have peace of mind that nobody else can write while we are reading, incrementing, and writing in one thread. So this is a very practical and easy way of dealing with race. Using this technique, what happens is that first thread 1 does the increment with peace of mind, and then thread 2 can read the result and does the increment without being worried that each of these two will corrupt the other's operations. So either thread 1 runs, then thread 2, or thread 2 runs, then thread 1, and not together at the same time. There would be no overlap. This also will address the problem of not having an atomic read, because the whole thing now would be atomic. So either thread 1 does its read, which can be multiple instructions, and increment and write all atomically, then thread 2 can execute and work on this variable, or thread 2 does whatever it wants to do, and then thread 1 can do it with peace of mind. The C++ standard makes this general statement that when one thread is trying to write inside an atomic variable and then another thread tries to read, the behavior is well defined. Basically, you would not have a race condition. That's what STD atomic guarantees. But if this is what STD atomic brings, and it's very simple, why everyone says STD atomic is so confusing and so hard to use? And that's because there's much more to STD atomic than just making the operations atomic. We will get to this soon. But before that, let's see what can be atomic. Almost all built-in types can be atomic. A Boolean, all integral types, including sign and unsigned, such as character, 16-bit characters, 32-bit characters, short, int, long, and long, they can all be defined as to be atomic. Floating point types like float, double, and long double can also be atomic. Pointers to anything can be atomic, and recently in C++20, smart pointers can also be atomic. So basically, you can define your atomic variables using STD atomic, and then inside these angular brackets, the type of the variable that you want. This one shows an unsigned int, a double, int star, which is a pointer, a boolean, or an unsigned long. Now, what if you define a class yourself? That can also be defined as an atomic variable as long as that class is trivially copyable. This trivially copyable is something that is formally defined in the C++ standard, which basically means, first of all, it has to be in a continuous block of memory so that you can copy the whole thing using a memcopy function, for example. It should not have a user-defined copy constructor, move constructor, or assignment operator, and there should not be any virtual functions in the class or in its base classes. So for example, you can define a class like this or a struct like this, and they can both be an atomic variable. C++ also provides this function is trivially copyable so that you can test to see if it passes this condition or not. Let's look at some more examples. So how about an STD atomic of a vector of integers? Can you define this or not? The answer is no, because we know that this class has its own copy constructor and other functions that violate this trivially copyable condition. How about this class? It has several variables and a constructor, a user-defined constructor. There's nothing wrong with this because it doesn't violate all those conditions. This class has a pointer. It's still okay. We can define this as an STD atomic. How about this one? This cannot be an atomic variable because it has a user-defined copy constructor. So you cannot define this. You cannot define an atomic variable of this type. And this one, it is a class. It has a function. There's nothing wrong with having a class that has a method like this. So this also can be a variable, an atomic variable. What can we do with std atomic? std atomic is a template that has member functions, constants, and some enumerated values which specify the memory orders. The member functions can be divided into specialized and general. Let's talk about the general ones first. This table shows the general member functions at a glance. First, you have the assignment operator. There's a member function that tells you if the atomic object is lock-free. We will talk about this later. Explicit memory access for loading and storing, atomic loading and storing in the memory, read, modify, write operations, and conditional variable functionality functions, which are being added as part of C++20. In this video, we will talk about all of them except for the conditional variable functionality, which are not completely developed yet. Defining and initializing. As we talked before, you just use std atomic, angle brackets, the type of the variable, the name of the variable, and that would be your definition. Right off the bat, there's a major confusion in defining and initializing an atomic variable. So you cannot define and initialize an atomic variable using the equal sign because it would not compile. In order to initialize, upon defining a variable, you need to use one of these alternatives. Either use parentheses, braces, or define first, initialize later. And this one shows how you can define an atomic variable using your own classes. Assignments. Again, right off the bat, there is a major confusion. You cannot assign one atomic variable to another variable using equal sign. This would not compile. And the reason is that std atomic is not copy assignable. So what should we do? You should either define one of them not to be atomic. For example, variable b is not atomic. Then you can say a is equal to b. Or you should use the explicit load and store. So here we're loading from B first and then store inside A. If you think about it, in this case, you're asking to read from B and write in A atomically. So we are asking to do two things atomically, whereas atomic variables can only perform one atomic operation on one variable. That's why this is not really possible. But in this case, what you're doing is first reading from B atomically, save it in a temporary variable first, and then atomically store that temporary variable inside A. So this is really two operations. Each of them is atomic. And then this example shows you can use assignment for user-defined, the classes that you define yourself. So for example, here we have the variable A, which is atomic. We have variable B, which is not atomic, and then we can assign B to A. Again, remember, A and B cannot be atomic at the same time. Explicit load and store. So if x is atomic and y is not atomic, you can either write y is equal atomic x to read from x, or you can write atomic x is equal to y to write into x. So you can either use this, or you can use explicit load and store. These two are really equivalent. There's no difference between them. So you can say atomic x.load is equal to y, or you can say atomic x.store, and then store the value of y inside x. So then the question is, if they are exactly the same, why do these exist? And the answer is that, like I said before, there's more to std atomic than just making the operations atomic. And we will talk about this later in this video, so please bear with me. For now, let's just know that these two are equivalent. All right, we talked about assignment, we talked about load and store. Next up, let's talk about exchange. Exchanging is simultaneous atomic read and write. Basically, from variable x, you're reading and writing at the same time. So if this is x, you're pushing a value, the new value goes inside x, the old value is sampled and comes out of x, gets sampled inside old value. So we are basically running these two lines atomically. And that's basically what exchange does. So here is an example. You can define atomic x, initialize it to 1, y and z are two non-atomic variables. We initialize them 2 and 3. And then we can say z is equal to atomic x, exchange it with y. So what would be the value of x and y and z after this line? Before doing this, x and y and z were 1, 2, and 3. Once you run this, the value of y would go to x, the value of x would go to z, and then the value of y would not change. Now, what would happen if y also was atomic? In that case, you can still do this exchange, but what happens is that again, the value of atomic y is read first, one atomic operation. Next, you do this exchange, which is a separate atomic operation. Now, what would happen if we also convert z to an atomic variable? So in this case, what happens, just like before, first we read the value of y atomically, then we do the exchange with x atomically. The result of exchange would be stored in a temporary variable, and then the final atomic operation would be assigning that temporary variable to z atomically. So in reality, this expression is a combination of three separate atomic operations: reading from y, exchanging with x, and then storing the result of exchange inside z atomically. Up next, let's talk about compare and exchange. Compare and exchange is another read, modify, write atomic operation, except that the modification and writing is conditional. Another name for compare and exchange is compare and swap. The way you use this on an atomic variable is that you call compare and exchange either its strong or weak version. We will talk about this in a minute. And then you give it two parameters, which is expected and desired. Now, what happens is that once you run this algorithm will get executed atomically. So we compare the value of x with expected. If it was expected, then we update its value to the desired value. And we return true, so success would be true. Otherwise, we update expected to this value and we return false. The important point is that this whole algorithm runs atomically. Now, let's see an example. Let's say atomic x is initialized to 1, the expected value is 2, the desired value is 3, and then we run this line to do compare and exchange with expected and desired. So before running this, x is 1, expected is 2, desired is 3. Once we run this, the first time you run this line, you will get false because expected and x are not equal. So we would be in the else part of this algorithm, expected should be updated to atomic x, so we update expected to 1 and we return false. Now let's say I run this one more time. In this case, expected and x are now equal, so we would be in this part of the algorithm. And then in that case, we update atomic x to desired. This would be updated to 3. Expected and desired would not change, and then we return true. Why do we need such a complicated operation, you might ask? Consider this function, which is relatively complicated. And let's say we would like to write x is equal to f of x, and we want to do this atomically. Compare and exchange helps us to do this, because in reality, if we didn't have this operation, we really needed to do load from x, then calculate f of x on the value that we loaded. So load from x, put it in a temporary variable, calculate f of this temporary variable, then store it again, and then store the value of f of t inside x. So there's three operations. If you wanted to do this atomically, these three operations should have been done atomically. And up to now, unless you use critical section and mutexes, we don't know how to write these three lines atomically, right? Every line can be run by itself. This line would be atomically, a load would be atomic, store would be atomic, but all of them together is what we want. And we don't know how to do this atomically yet. We would like to take x, calculate f, replace it by the value of f of x, all of this atomically. Now, let's see how compare and exchange can do this. Let's say we want to do this in thread 1. So basically, we define x to be atomic, and we write atomic x is equal to f of atomic x. Also, assume there's another thread, thread 2, which tries to write inside atomic variable x a new value called value 2. So what happens now is that if we want to do this atomically in thread 1, we read from x. Let's say we read the older value, which is value 1. Then we calculate f of x, and we want to store f of value 1. Now, what happens if this store gets executed after load? It writes value 2, but we read value 1 and we are calculating f of value 1. So if we store with f of value 1, we kind of missed this value 2, and that would be undesired. It would have been great if during this time we could have detected that somebody else wrote inside x, and we could have taken the latest value of x and calculate f of value 2 instead of f of value 1. And that's how compare and exchange can help. This is a very common pattern of using compare and exchange. For thread 1, rather than writing this, we can write this. So we first read the value of atomic X, we load the value, which is value 1, and then we run compare and exchange in a loop. Let's see exactly what happens in this loop. So if store happens after load, the stored value is now updated to value 2. We read the previous value of X, which is value 1, and that exists inside the expected value, which we call it old X now. And then what we want to do is to update to f of value 1. That's what thread 1 wants to do, but thread 2 came along and wrote value 2. Now, compare and exchange can detect this because value 2 is not value 1, so we go to this part of the algorithm, and in this case, we don't update g atomic X. Instead, we update expected to be the value of atomic X. So basically, we update this expected to be the value of X. So now the expected value is value 2. Now we run this one more time because in this case, we return false because the two values were not equal. We just update expected and we return false. Now, next time that you run this, value 2 for X is equal to value 2 for expected. Therefore, we are in this part of the algorithm. We update atomic X to be the desired value. In this case, the desired value is f of old X, f of value 2, which is really f of value 2. So now we can go ahead and update f of value 2 to X and return true. The loop exits. So you can see if store of T2 happens after load, although we read value 1 first, we detect this change while we are doing this calculation, and we are able to take this most updated value and store it in X. This is very powerful, and it was not possible if we didn't have compare and exchange. Now let's look at the case where T2 happens before load. So T2 will go ahead and write value 2. After that, T1 tries to load. So in this case, we really see value 2 from the very beginning. So the first time that you run this loop, value 2 of X is equal to the expected, which is also value 2. So therefore, the very first time we go ahead and write value 2 inside X and update it to f of value 2. Again, in this case, we were also able to write the latest f with the latest value of f of value 2. So all I'm saying is that for one thread, instead of writing this, when you want to update an atomic variable to a very complicated function which you cannot implement atomically, rather than writing it like this, which may have race, use this pattern and use compare and exchange. So in compare and exchange, you first read the value and then you modify and do your calculation, in this case f of X. But before updating, you check to see if somebody else has modified it. So you detect if there was a change. Only if there was no change would you go ahead and update the value. Otherwise, you detect, update to that new value and then do this in a loop and keep doing this until you get all the updated values from multiple threads, if you have multiple threads changing this atomic variable, until there's nobody else to change it, and then you can write. Now let's talk about the strong and weak versions of compare and exchange. There are two versions. You can say compare and exchange strong or compare and exchange weak. There's really not that much of a difference in functionality between the two, except that compare and exchange strong does not have spurious failures. However, compare and exchange weak has spurious failures. Spurious failure means even if the value is expected, even if the condition is taken, you might fail without an update. If you have a loop, this would be okay for compare and exchange weak. Otherwise, this would be wrong. So the recommendation is that whenever you have a loop, use the weak version because this weak version is potentially faster. Otherwise, if you're outside of the loop, always use strong. Up next, there's yet another big confusion for STD atomic, which is if it's implemented using a lock or not. Loosely, when you don't use mutexes, you call that lock-free programming. But this, in reality, does not hold. The standard mentions two important things about atomic variables. Number one, all atomic types except for STD atomic flag, which I didn't cover in this video, may be implemented using mutexes or other locking operations instead of the lock-free atomic CPU operations. So this is very important because any variable, either built-in or your own types, when you set it to be atomic, it may actually use locks behind the scene, although you still call it lock-free programming. So yes, that's a confusion, but as far as we are concerned, as far as you think about atomicity of operations, you can basically not care if they are being implemented using locks or not. The standard also mentions another important point, which is atomic types are also allowed to be only sometimes lock-free and then sometimes not lock-free. So the same type. So if I define a variable of this type, it may or may not be at sometimes lock-free, sometimes not lock-free. And this is related to how this variable is aligned in the memory. If you care about this, the standard provides these two functions to detect if a variable or an object is lock-free or not. Basically, I can write for these two variables a and b, I can print out if they are lock-free or not. This is a method that's run in runtime, and it prints if this variable is lock-free or not. These two pieces of code basically do the same thing. So you can either use this form or call the object method. Now, if you want to find out if a certain type is always lock-free, use this constant. So remember now, this was a method, a member function. This one is always lock-free, is a constant, which has a value during compile time. And basically you can find out if a variable of this type is always lock-free or not. We talked about general methods. We just talked about constant, which is always lock-free. Up next, let's talk about specialized member functions on std atomic. This shows the specialized member functions at a glance. So we have several functions that they fetch the previous value and then they apply an operation. So for example, here, fetch add and fetch sub mean read the value, the old value of the atomic variable, and then add something to it or subtract something from it. We have similar operations for AND, OR, and XOR. And then we have increment, both prefix and postfix, decrement, prefix and postfix, plus equal, minus equal operators, and their logical equivalents. Fetch, add, and sub only apply to integral types or floating points or pointers. The logical equivalents only apply to integral types. Increment and decrement apply to integrals and pointers, but not floating point. Plus equal, minus equal applies to integral, floating point, and pointers, and their logical equivalents only apply to integrals. Notice that none of these apply to Boolean type. That's why we call them specialized. So these are specialized member functions for different types. Let's quickly talk about fetch add. Here, we have two functions. One of them uses the plus plus operator. The other uses fetch add and 1. These two are really equivalent. Basically, both of these will increment atomically. If I run multiple versions of these two functions in parallel, what I see is that the value of data 1 and the value of data 2 is equal. So in this case, I'm running 5 copies of each of these two functions. Each of them increment once. This one increments data 1, this one increments data 2. After 5 threads of work 1 and 5 threads of work 2 are finished, data 1 should be equal to data 2 to value of 5. So basically all I'm saying is that these two are equivalent. So let's look at these operations a little bit more closely. For example, when you write y is equal to plus plus x, what you really say is that atomically increment x, then read its value. So that means increment and reading is done atomically. You can implement the same thing, the same result, by writing this expression here. It's important to note that this expression here is not equivalent to first doing x is equal to x plus 1 and then y is equal to x. Because what is happening here is that you really have multiple atomic operations running sequentially. So you first read x, then you add 1 to it, then you store the value back to x, then you load from x, and then you write it inside y. So this expression is really 4 operations. However, this one is just one atomic operation, which is increment and read x. And then afterwards, you assign it to y. If plus plus, minus minus, and plus equal and their logical equivalents exist, why do we have these fetch versions? So again, the answer to this question is that because std atomic is more than just atomic operations, and we are very close to explain what that more functionality that std atomic has is. So please bear with me a few more minutes and we get to that. So for now, operation wise, these two are very equivalent. So you could either use these operators, plus plus, either prefix or postfix, minus minus, and then plus minus, minus equal, and their logical equivalents, or you can use the fetch versions. Just make sure that you don't confuse them with these versions. They are not equivalent because what happens here is not atomic, but what happens here or here is actually atomic. Now, before getting to this part, which is what exactly this std atomic is providing beside having atomic operations, let's quickly review and see what exactly we learned so far. So we learned that we could either use assignment or use the load and store explicitly. And then we learned that there's a set of generic member functions. It is lock-free, load and store, exchange, or compare and exchange either weak, or strong. These operations apply to all atomic types. Then we learned about specialized members, which only apply to certain types. For example, fetch, add, and fetch sub only apply to integral, floating point, and pointers, but not booleans. So here is a summary of all of these operations and what types they cover. Basically, it's a repetition of what we just said. Up to this part is the generic member functions. It applies to all types, and then afterwards it becomes specialized. So for example, logical operations do not apply to pointers or floating points. Also, we learned that we should get fooled by these kind of expressions, that whenever you write multiple expressions on an atomic variable, you should pay a lot of attention to make sure what you mean is exactly what gets executed. For example, in this case, we saw that this one line is actually multiple operations which do not run atomically together. We have talked about all of these features of SCD atomic. The last section of this video talks about memory orders in C++, which is also used by SCD atomic. So remember that we kept saying that there's more to SCD atomic than making operations atomic. This is a section that we're talking about what exactly do we mean by these more features, and let's talk about it. Let's start with one formal definition in C++ standard, which is sequence before. Sequence before has a very formal definition in C++ standard, which you are welcome to go and read the details, but it really tries to capture what we commonly know as program order. Basically, when you write a program, you expect one expression to happen before or get executed before the other expression. For example, here by semicolon, we explicitly want expression 1 to be executed before expression 2, and then expression 3, and then 4, and so forth. This is defined within a single thread. So this sequence before relationship exists. It's defined formally, and it exists in one single thread. But what happens is that the compiler or the cache or other parts of your system may reorder these things for optimization. However, as they reorder them, the result of reordering should feel or seem to be the same as the original. So basically, your compiler, your cache, or whatever optimization you perform here is free to do whatever they want, as long as what we print here is still valid. So basically what we want is an illusion of sequencing. So for example, all these values here, x, y, b, and flag are initialized to 0, and then we run this code. The output should be message is equal to hello world, and then the value of b is 1 plus value of flag, which is 2, and then the value of y is its initial value, which is 0, plus the value of 3, which is 3. So this is the valid output that we want for our program. Now your system may reorder this in a different way. So flag becomes 1 here, and basically this operation has moved all the way to the top. This operation has moved all the way after flag is equal to 1. And once you run this, although this is a different reordering, you still get your valid output. So your compiler is free to perform this reordering if it wants to. Now let's look at another reordering. So here we moved this y plus equal to x to all the way to here, and then b plus equal to flag all the way here. And what happens is that this reordering is not valid anymore. Once you run this, the value of b would be 0. Once you run this, the value of b would be 0, the value of y would be 0, which is not the valid output that we expected if the sequence was forced. Therefore, we are telling our compiler that you can have your own privacy, you can do all the reorderings that you want, do whatever you want here, any crazy reordering that you want. As long as you don't generate something that is invalid, we are fine with it. And as long as this correct output is created, everything is fine. Now, once you go to a multi-threading environment, what happens there? So we mentioned that usually we have this privacy, we give this privacy or freedom to our compiler to do whatever it wants here. And that's because we don't really look inside the thread. We just look at this point and observe the effects at this point. And the compiler has promised us that it doesn't violate the correct result. So as long as we only observe here, everything is fine, and the correct result will be printed. However, once you have other threads running, it's not just us observing. Other threads also observe at the side effect of the operations that are happening here. So this privacy really will go out of the window. So now if I reorder, if another thread looks at my execution, if another thread looks at the execution of this thread, it will see that flag became 1 before this message being assigned to hello world being assigned to this message. Therefore, we can say in multi-threading environment, one thread can see through other threads. So this reordering now becomes a big deal. It wasn't before in a single thread. You could basically do whatever you wanted as long as you have the correct output. You have this. Your compiler could enjoy this privacy and do whatever it wants. But as we move to multi-threading, this privacy goes out of the window. And basically, if it does reorderings that's still valid for this single thread, it might break other threads, and we'll see how this is happening in a second. Now let's see how this is happening. So we are talking about the side effects of reordering. Let's say I have this original thread that's executing my valid output like this, and I have thread 2, which is monitoring flag, and then only after flag becomes 1, it samples message and assigns it to text and then prints it. So then the output of thread 2, the valid output of thread 2, we expect it to be hello world coming from message. So this thread really sees flag being 1 as a token, as a sign of message being hello world. That means if I reorder this thread to something like this, now flag being 1 doesn't have that implication of message to be hello world anymore. So that means by monitoring flag equal to 1, the output now would be invalid. It's not hello world anymore. It's just an empty string. It would have been great if we could have told our compiler that you're still free to do all the reordering that you want, as long as you don't do this reordering, which breaks thread 2. Although, notice that this reordering for thread 1 is still correct. It still generates the output that we expected. So if it was only a single thread, thread 1, this reordering would have been valid. But now that we have thread 2, only one of them is valid, the other one is not invalid. And the big picture here is that we are learning how stdatomic comes to help us to tell our compiler that only keep this reordering and not this reordering. And we'll talk about this in a minute. Before getting into details, let's talk about some relationships that are defined in a multi-thread or multi-processor environments. The one famous relationship that's defined is called sequential consistency. So sequential consistency states that if you run these two threads together, it would be as if all of these operations were run in some sequential order. Within each of these threads, it's as if they were running in program order. So one more time, it would be as if all of these operations, there is a total order between all of these operations. They appear in some sequential order. The second one states that within each thread, it appears that the program order was honored. So basically, you might get this ordering, or you might get this ordering. The order within single thread always should appear like 1, 2, 3, 4, 5, and then A, B, and C. But the order between the two threads is not defined. So within every thread is program order. Between threads is not defined. The only thing that we say is that it should appear in some sequential order. So for example, here, some sequential order is 1, 2, A, 3, B, 4, 5, 6. And then another sequential order might be 1A, 2, 3, B, 4, 5, C. C++ standard defines another relationship formally, which is called happens before. Happens before is generalization of sequence before or program order that we saw before. And it's defined as follows. If A and B are operations now in a multi-threading system, if A happens before B, then B should see the side effects of A. By side effects, we mean if A writes something, B should see it. And as we mentioned, sequence before was defined in a single thread. Happens before is a generalized form of sequence before, and it's defined between multiple threads. And if you have a sequence before relationship between A and B, that also implies that they also are in happens before relationship. Basically, 1 is sequence before 2. It's also happens before 2. 2 and 3 are in a happens before relationship, 3 and 4, 4 and 5. And here there's A sequence before B, also happens before B, and so forth. So far, we haven't defined anything interesting yet, but what if we could somehow provide a bridge between thread 1 and thread 2 and mention that, or force that, this expression 4 is happening before expression B. What if we could force this? As soon as you have this bridge, what you can say is that, okay, I knew 1 is happening before 2, 2 is happening before 3, 3 is happening before 4. Because I have this bridge, now I can say 1, 2, 3, and 4 also are happening before B. Basically, you can say 4 happened before B because we just forced it. 3 happened before 4 because of this sequence before relationship or the program order. From these two, I can deduct that 3 is happening before B. That means I can deduct correctly that if flag becomes 1, it means that message is assigned to and it has the correct value. And the thing that we are mentioning here is that what if we could force the compiler to assume this relationship exists and then does its reordering while honoring this happens before relationship. That's a very powerful thing that we are asking from the compiler. And basically the big picture here again is for us, how stdatomic will provide this bridge for us so we can happily do these deductions. And what that means is that while you're telling your compiler to force this, That means we're telling the compiler not to do this invalid reordering, although this reordering would have been valid in a single thread environment. In the next few slides, we talk about how we force this bridge. For now, let's just assume we magically create this. One last relationship that we want to define is called synchronizes with. Synchronizes with is defined formally on suitably tagged atomic read and write operations on one atomic variable x. For now, let's forget about suitably tagged. Basically, synchronizes with means if you perform a read and write on variable x, this read and write or load and store are in a synchronized with relationship with each other. That's the first thing that synchronizes with is defined. The other thing that you need to know is that synchronizes with implies happens before. And that is the very powerful thing that atomic variable is providing. Basically, it says the store here, if flag was atomic, we are storing 1 inside flag. It mentions that this operation 4 is synchronizing with operation B. Because we know that synchronize with also implies happens before, basically, you could now do those happy deductions and prevent this invalid reordering and say, I know that 4 is happening before B because they're synchronizing with each other because it's a load and store in the same atomic variable. And I knew that 3 is happening before 4 because of program order or sequencing or sequence before. And now I can happily say 3 is happening before B. Therefore, this message should be forced to have the correct value, and compiler cannot do this reordering. So basically, you need to change your global variables to atomic. We make them atomic for 2 important reasons. The first reason, which we talked in the first section of this video, was because you're sharing them, you're reading and writing from multiple threads, you make them atomic to prevent race. The second reason that we're talking about here is that we want to form this bridge between these 2 threads so that the store on flag and the load on flag synchronize with each other and do this happy deduction of 3 happening before B, have a peace of mind that whatever the compiler does here, this deduction still is valid. I can still make sure my output prints the correct value. I know we talked about multiple relationships and it might become confusing, so let's review them quickly and see what we learned. We learned happens before relationship between 2 operations A and B. So basically, we say if A happens before B, B will see memory effects of A. So if A writes something, B should observe that. We also saw that sequenced before is a relationship within a single thread, and then synchronized with is a relationship between multiple threads. And these 2 also imply happens before. So synchronized with between multiple threads and sequenced before within a single thread help us to do deductions. And for example, here we can say 1 was sequenced before 2, 2 was sequenced before 3, 3 was sequenced before 4. Now this synchronization helps me bridge to the second thread and then say 4 happens before B. And then this bridge helps me go from 4 to B in this thread and still say 1 happened before 2, 2 happened before 3, 3 happened before 4, and 4 happened before B, and B happened before C. This single bridge here is a very powerful tool for us to still have valid input, force valid input in thread 2 and be able to reason about our code. We kept talking about suitably tagged atomic operations. Let's see what these tags are. So remember that we said you could either use equal sign for load and store, or you could use explicit load and store methods. And we said these are equivalent. However, what we didn't mention yet is that load and store can take one optional parameter, which is the tag for that atomic operation. So that tag specifies what memory order you want to use. And we have various tags. The ones that we talk in this video are relax, acquire and release, and sequential consistency. Sequential consistency is the default, which means in this case, you have the sequential consistency tag. This tag here is implied. And here for load and store, if you don't put the parameters, you have, by default, you have sequential consistency tag. Sequential consistency is the strongest. Then there's acquire and release. And then the weakest one is relaxed. We will talk about what we mean by weak and strong in a minute. Let's talk about memory order sequential consistency. As we have seen before, this 2 operations, load and store, can be done by equal sign. It's equivalent to use load and store explicitly. It's also equivalent to use load and store with this sequential consistency parameter. Because this was a default value, this was also valid. This is also the default the equal sign also by default uses sequential consistency. What do we need to know about memory order sequential consistency? The first thing is that it is very powerful because it's providing the synchronizes with relationship. As soon as you have a store on one thread on this atomic variable and you have a load on another thread on this atomic variable, they synchronize with and they form this bridge so we can have peace of mind and reason about our code. And basically, it's a very strong feature that C++ is providing and tells us, hey, as long as you use this tagging for flag and do this load and store, I make sure that I don't do reordering here in a way that breaks your code. You want to keep this happen before relationship between these two threads, so I'd be careful not to do this. So this is the main reason that one would use sequential consistency, but it also provides another very strong feature, which is that all the threads would agree on ordering of operations. Basically, sequential consistency puts a total order on all the operations among all the threads. As we talked about this before, when you run this, it is as if there's a total order between the operations of this guy and the operations of this guy. There's a famous example in C++ standard for demonstrating what we actually mean by this total order. So imagine I have 4 threads and I'm running in one thread, I'm writing inside X to be true. In the other, I will write inside Y to be true. In this thread, I'm reading X, then reading Y. That means I wait for X to become true. And then if Y was true, I increment Z. In this thread, I do the opposite. I wait for Y to become true. And then after, if X was true, I increment Z. And we assume that X and Y start from false and Z starts from 0. Now the question is, can this assertion fire? Can Z, after running all of these threads and joining them, can we have a case that Z be still equal to 0? You're welcome to pause the video at this point and think about if this assertion can fire or not. So let's see what can happen. It can happen that X, write to X happen before write to Y. In that case, in this thread, we are waiting for Y to become true. So by the time that we perform this condition, we sample X or load from X. Because Y, writing to Y happen after X, we know that this condition will be taken. So Z plus Z will be executed. So Z cannot be 0. The assertion would not fire. So it's either this case or the other case, which is writing to Y happens before X, which by symmetry means that increment of Z should be executed, therefore this assertion cannot happen. Therefore, in both cases, the answer is no. But with sequential consistency, we also force the two threads to agree on this ordering. So if Y happens, if one thread sees Y is happening before X, the other thread also sees Y is storing to Y is happening before storing to X. Because and only because we have this agreement can we say the answer is always no, because both threads agree that either X happened before Y or Y happened before X. So either here we increment Z or here we increment Z, and we can say that this assertion never fails. So there might be a case, we will see it in a minute, that if you don't use this tag, these two threads, although Y happened before X, although this happens externally in reality, there might be a case that these two threads do not agree on this ordering, and this assertion may fire if you don't use this tag. Now, for most programmers, this second feature of sequential consistency is not that important. It's not that useful. What is mostly useful is this synchronization and this bridge that it creates. Basically, in most applications, what you really need is this bridge, the global total order of the operations, or the agreement between the sequence of operations, is something that you may or may not use. It's something that it may or may not be useful to you. So it's something that it's something that sequential consistency provides on top of this synchronization relationship. Now let's go to the other extreme, which is memory order relaxed. To make the story short, memory order relaxed is still atomic, is still an atomic operation when you tag it as when you tag a loaded store to be memory order relaxed. It just doesn't have this synchronization relationship. So if you want to store inside message the same hello world value and mark it as relaxed, you should use the explicit store, and then we do explicit store for flag. Also, if you want to use flag, if you want to use memory order relaxed, we should use the explicit store, and then we do 1, relaxed. On the other side, we do the same. So we load using this tag for both flag and for message. The operations are still atomic, but this synchronization doesn't exist. That means the compiler is free to do some reordering here, reorder 2 and 1, and basically what happens is that we might get wrong answer. Let's look at this more closely. So we are storing hello world inside message, and we're storing 1 inside flag using memory order relax. And by that, we allow the compiler to perform this reordering. So basically what happens is that now flag might become 1 before message has the correct value. Therefore, as I'm waiting for flag to become 1, message may not have the correct value and I might get an incorrect result. So the important thing to take away is that memory order relax does not have this synchronization. It also wouldn't have that total order that sequential consistency was providing. So let's go back to this example that we saw before and replace these tags by memory order relaxed. So now they are relaxed, and let's see what happens when I execute this. So basically the question is, can I run this and see the value of z to still be 0? And the answer is simply yes, because there's no total order anymore. So we cannot do the same reasoning that we did before to say it's either x happening before y or y is happening before x. One thread might say x is happening before y. The other thread might say y is happening before x, and therefore for both of them this condition may not be taken and this assert may fire. Up next, memory order acquire and release. We talked about relaxed, we talked about sequential consistency. There's something in the middle that's called acquire and release. As we saw before, sequential consistency provides synchronization and total order. Acquire release is a little bit weaker and it only provides synchronization. And then there's relaxed, which provides neither synchronization nor total order. The first thing that you need to learn about acquire and release is that they come as a package. That means there has to be a store on an atomic variable that is tagged as release, and then there has to be a load on the same atomic variable that is tagged as acquire. And these two always come in pair. Store with release on one thread and then load with acquire on another thread. And then the other thing is that release always comes with store and acquire always comes with load. Now, as we mentioned, acquire and release provides this bridge which it synchronizes with, and we can happily still do all these deductions that we used to do before and reason about our code. And also, as we talked before, because total order doesn't exist anymore, if you run this and mark your atomic variables, atomic operations as acquire and release, this assertion can still fire because there's no total order the same way that it was with sequential consistency. Another way to understand acquire and release is to consider them as one-way barriers. So consider thread 1 that is running and it assigns to message and then it assigns to flag and releases this value, and then thread 2 which is loading this value with acquire flag. You can consider the release here and the acquire here to be a memory barrier. Basically what it means is that this barrier prevents things or operations to go from before to after, but anything from after to before is correct. In particular, assignment to message from before the store cannot be reordered by the compiler to after, because otherwise the sampling here would be wrong. By symmetry, sampling or reading from message should be done after loading the flag. It cannot be moved up here, because if you do that, then you will sample the wrong value. So this is how you force your compiler not to do these reorderings. Another way to look at this is to remember what critical section was, as we studied it in my previous video, in which a critical section forms by locking on a mutex and unlocking the mutex. What happens in the middle is inside the critical section. And in general, it's okay to move operations inside the critical section, but it's not okay to move them outside of the critical section. That will be an incorrect result. Acquire and release can be considered each half of this critical section. Basically, a lock functions as acquire and unlock functions as release. What happens on the left for release is that things are okay to be moved inside this half of the critical section, but things cannot go, the memory operations cannot go down. And by symmetry, on the right side, it's okay to move things, move operations down the barrier, but it's not okay to move it up. So for example, if you have a read operation here, if you move it up, your read will not see the result of this write on the left side and you get an incorrect value. So this reordering is not correct, and by tagging your memory operations, you're telling your compiler not to do this. And similarly, on the left, you're telling your compiler not to move this write, because if you do, then the happens before relationship between this write and this read here will break, and then again, you get incorrect results. So again, we are preventing our compiler not to do this reordering. Now, it's worth going back to mutexes and critical sections one more time. The standard mentions that unlock on one side performs release, and the lock on the other side performs acquire. So this unlock and lock are synchronizing with each other. The result of all the memory operations before unlock are going to be available for whatever comes after lock. And if you remember, when you use conditional variables, you use a lock, which does a release, and then a wait can do lock or unlock, depending on if it gets blocked or not. But if it does lock, then it does acquire. And then again, this synchronizes with relationship exist. And that is why we can assign something to data and then sample it on the right side. That is because this synchronizes with relationship exist. Therefore, the result of storing something in data will be available on this thread. There's one last memory order that we talk about, which is acquire and release. So this is a tag that does both acquire and release at the same time, and it's used for read, modify, write operations. If you remember operations like exchange, they read, they load, they modify, and then they write the result back. So when they load, they do acquire. When they store, they use release. And finally, there's compare and exchange, which takes two memory tags, success and failure, where if you remember the algorithm, the high-level algorithm for compare and exchange was something like this. But if you want to tag them, if you want to specify tags to be non-default, you specify two more parameters. And the way they work is that if this condition is taken, in which you are both reading from atomic X and then write back the desired value inside of it, this read, modify, write operation will be tagged as success, whatever this success parameter is specifying. And then if this condition is not taken, we're still loading from X. So that load is specified by this failure tag. If you want to put everything all together and look at a summary of what we learned so far, so you have a variable that can be non-atomic. So there's no atomic operations, there's no synchronization. The compiler can reorder it, and there's no total order between the operations. All threads may not agree on what non-atomic operation happened after or before another non-atomic operation. Then there was memory order relaxed, which is atomic. It does not provide synchronization. The compiler can completely reorder it. It's free to reorder it, and there's no total order. Then there was acquire and release. It is atomic operation. It provides synchronization, and then as a result, there's no reordering, and there's no total order. And then the strongest one was sequential consistency, which is atomic. It provides synchronization, compiler cannot reorder it, and it provides total order. We learned about atomic operations and memory orders, but then the question is, why was the motivation of using atomic operations? Was it because they were easier to use, or was it because they were faster? And the short answer is that probably they might be faster, but you have to be very careful and you have to benchmark your code. And you also have to make sure that you do a fair comparison between atomic operations and perhaps the other alternative, which was using mutexes. In order to understand this, let's look at this great example from CPPCon 2017, in which you can assume there are multiple threads. Each thread will run this code, basically counts from low to high, and then each time increments a global variable, which is atomic. So there's no race because it's atomic, and you're basically, each thread is counting from low to high, and add that count to the atomic sum global variable. Now, an alternative to this is to use a mutex. So to this function, you still pass low and high, you count from low to high, and then you store the count in a local variable. Once the count from low to high is done, you write it in a global variable. The global variable is not atomic anymore, but instead is protected by a mutex. So still, there's no race, and the result of this code is equivalent to the result of this code. They both generate correct result. Now, the question is, we used atomic operation here. Is this faster or slower? And the best way to measure this, see the result, is to benchmark this on your own system. So if you do this, chances are you see a result like this. So these are the number of threads. This is the runtime. And you will notice that using the atomic variable, the runtime gets worse and worse as you increment the number of threads. However, for the mutex, the runtime slowly drops, and basically you can see that the atomic operation is much slower than the mutex operation. And this can be very confusing because we normally think that atomic operations are usually faster than mutex implementation. Now, why is this happening? Let's go back to the code and see what exactly is happening here. So on the atomic implementation, we access the atomic variable, the global variable, each time in the loop. And that's a lot of accesses. However, in the mutex implementation, what is happening is that you first count in a local variable, so you don't lock or unlock, no thread will wait for the other thread in critical section. Only when this counting is done do you go and write the result in the global variable, which is protected by mutex. So it's obvious that the atomic implementation is very suboptimal. Basically, what's happening is that because you're doing a read, add, write for each increment, by definition, these three cannot run in parallel. Basically, because they're atomic, they have to run in series. And that means, although you're doing multi-threading, the operations are actually running serially. So there's no parallelism and you don't gain anything from multi-threading. And what it's worth is that because each thread has to wait for the result of the other thread, we pay for the penalty of going through all the caches to the memory and then come back so that this thread here can send the result of the calculation to this one. Obviously, this was not a fair way to compare atomic implementation with mutex implementation. So you should always be careful that you do this comparison in a very fair way. One way to fix this and make the comparison fair is to use the same method. So first count from low to high and store the value inside the local variable. Only when this is done do we go ahead and add it to the atomic global variable. These two still generate the same result. And now this is a little bit improved. We call this atomic accumulator partition. So if you benchmark these two now, you will see that the results are very similar and the runtime drops as you increment the number of threads. And if you want to put things in perspective, this one is the first atomic implementation that we saw, which you access the global variable in each iteration of the loop. And these two here are very close. The atomic implementation where you first write inside the local memory, and the similar mutex implementation. So what are we saying here? There are multiple lessons to learn. First thing is that you need to run your own benchmark on your own system to figure out exactly which operation is faster and slower. And then as you do this, make sure you do fair comparisons and understand your algorithm. So just because you use atomic doesn't mean that your program runs faster. Chances are you use the wrong implementation of atomic and you don't gain anything. So just using atomic operations doesn't mean that your program runs fast. And finally, your goal should be to minimize the use of either atomic operations or critical sections. No matter which one you're using, you have to make sure that you try to minimize operations that require lock or unlock in critical sections or require to be atomic. And one example of this was using the reduction technique that we just saw here, where you can use a local variable, and then once you're done with your result in the local variable, then you go ahead and reduce all the local variables from threads inside the global variable. One last thing I want to talk about is to be careful whenever you're using these common and familiar patterns to tag your atomic operations correctly. For example, whenever you are using this pattern where a flag indicates something else happens, for example, a memory location was written, in that case, you need a synchronizes with relationship, which a release and acquire seem to be a very suitable tag. You definitely cannot do this with memory order relax, and memory order sequential consistency might be too much because you may not need the total order. Similarly, when you're using something as a counter, you probably should tag it as memory order relax because you don't need synchronizes with and you don't need total order. So here we are using the default tag for atomic sum, and that means the memory order sequential consistency will be used. It's probably better to modify it and use explicit fetch add with the tag for memory order relax so that whenever anyone reads this code knows that you don't need synchronization. And that's it. Thank you so much, you guys, for watching this video. I hope this was useful to you. Please go ahead and let me know in the comments if you have any questions. Make sure you like this video and subscribe to my channel, and hopefully I'll see you in the next videos.